Yeah, it's get the initials that are the true initials once they've been diluted. Of the two reactants as well. Because what you have to start with is your I of iron, your I of thiocyanate, and your E for the FeSCNO or FeSCN2+. So you have like 2 data points in that final one. You also know you have 0 for the initial product. You're looking for the changes and then the final equilibriums of those other 2 reactants.
What happens if you don't have the K value?
That's what you have to get your equilibrium values and then you're gonna plug them into the K constant to get the K value. You already know your change.
Yeah, we do.
You're good. You got everything you need. What's up? Oh, you good? You left a green pen in that bucket over there someplace too.
I did?
Yeah. That one you're looking for?
Probably yours.
No, I don't care. Take it. I'm a pen thief. I just steal pens. Yeah.
By the way. I'm fine, man.
I love food and coffee. I'm easy.
Oh, I was thinking circle.
Yeah, so the circle is that.
Is everybody okay? Yeah? Okay. Yes, and you'll average your K value at the end. Yeah, I told you the net absorbance. Your differences from that first trial with no thiocyanate added would have been giving you the one to subtract. I just gave you my nets. So just scratch that out of the chart. take I'm still solving problems on the board just for fun, so take another 3 minutes.
She was like trying to get on the shot. So I just
Alright, finish that last part you're working on, come back to me when this thing goes off beeping. Did you get to a place where you understand where you're going next? Yeah. Where is it? All right, and you're coming back up here with me. I'll recap the lab one more time, and then we're talking about neglecting X. How you're neglecting X problems out. Let's go. So, quick talk about that one more time. I know the first time I did the lab, I was trying to think about why I was doing what I was doing, and it took me a minute to figure out why I was doing what I was doing. So sometimes that needs to be talked about. So you guys just saw that we calculated the initial concentration of iron 3 for all the 4 trials. What was it?
It was 6 times 10 to the negative 4.
Molar, right?
Molar.
And the thiocyanate CN1 minus was different for all 4 trials, but you found it the same exact way you found the iron. What was your initial concentration for the first, or sorry, I guess trial 2?
4 times 10.
4 times 10 to the negative 4th. Did anybody else get that? Okay, thank you. So then that equilibrates to FeSCN2 plus, which initially before the reaction has to be 0, right? You know we don't have that. But after the reaction, I gave you my absorbance, which you took my absorbance and you found your own calibration curves concentration that correlated that. Corey, did you guys do that?
For what?
Did you correlate the 0.09?
Yeah.
What was your
For
concentration?
2, it was 4.94 times 10 to the negative 4. Using our slope.
Your slope. But other people's will be different. Did anybody else get one? Yeah.
5.5 and
So similar, right? So we should be kind of in a similar boat. Binky?
Not.
Got it. What's your as a slope?
Yeah, so we're not sure how everyone got there.
Do you know? So you don't know how to get here. Is that what you guys are
We
saying?
got to there.
So give me a thumbs up if you can get from my absorbance get to your concentration from your calibration curve.
Oh, yeah,
for
we got
equilibrium.
there.
Okay, you guys can do that. Okay. So then once you're here, you're like, what the heck do I do? Well, you already know the change. What was the change? What was C? This,
Yeah.
right? You're adding it here. You're adding X. Well, you're basically saying what's X. You know that this is X. That means that you subtract X from both of these because it's a 1-to-1 ratio. You're subtracting that amount from both of these to get your equilibrium values, which you need to plug into your K expression. So if once you know your end concentration, you already know what you're subtracting here. So then that's going to be, oh, I can't do that in my head. 1 point. Okay, what is this concentration for yours?
5.506 times 10 to the negative
4th?
Yeah.
I don't know.
That's why
If you're subtracting
Yeah. Okay. You guys can math. And then this other number. Okay. Yeah, 3.5.
3.506 times 10 to the negative 4.
Okay. So once you know your molarities for equilibrium, and you know your K expression, which is products over reactants, plug, chug, K value. Got it? Say yes or no.
Yes.
Okay, I just need some feedback. So once you can get that for trial 2, you can do it for trial 3, 4, and 5. Once you get all of your K values with your concentrations being plugged in, you'll do an average. Yeah.
So the only thing that we changing for different trials is the amount of percentage, right?
Yeah, this will change because you have different amounts for each one. This will change because you have different observances for each one. Meaning this will be different for each one. This is the only thing that's staying the same because we walked about it on the iron because it's a constant throughout the experiment.
somebody burned something.
Huh?
Somebody burned something.
Usually I can spell that. Okay. So let's bounce to neglecting X. The neglecting X 4 problems. Those should be on your desk. Let me see those. Hold them up like this. Yeah. I want to see these before I begin because I'm not wasting my time if you don't have anything to already talking about.
I got 36 early. I get 36. The one, this one's wrong. I don't have to. Was it the one?
Yes, that Okay, well, let me see quickly.
Oh, here you go. My first name is Cody. I was a baseball practice. His name is Brian Rodriguez Cannon. This is like after school. I have to get right down.
I know what I need. All right, I'm trying to save your weekend, so work with me. Thank you, Levi. So today we are going over homework, neglecting X. I'm going to do 1 and 2 specifically. Things crunched already. I have more complex problems I'd like to get to. We're going to try to get there. Le Chatelier's principle is something that you learned a teeny bit in honors chem, but I can't depend on that because I have teachers leave twice. So I need to go over Le Chatelier's principle pretty in depth, and there's a web quest associated with this. My goal is for you to really only have to do the web quest to finish it up. But it's a flash or a shockwave based animation, and I can pull it up on my computer, but don't know if you can pull it up on yours. So I need to get to that, so that's important for me to do with you guys today. Neglecting X, here we go. You guys had the opportunity to set up your problem. You did. You got to the place where you were likely canceling out water because it's a liquid. Okay. You plugged in your initials. You plugged in the subtraction component, which because you were given 0 and 0, or you weren't given any information about both your products, you subtracted X, added X. Down here, it's getting pretty crazy. You got a lot of X's, a lot of 7th powers and 5th powers, and you're not likely going to be doing that math. So you're probably going to be neglecting X. The key sign to that was probably the negative 13th power here, which was also like, hey, probably going to neglect X. So once you see your expression with your 5ths and 7ths and everything like that, and you see that you're likely going to neglect X, I just neglect it here to show it's approaching 0, and don't plug it in here. Or here. So then 5 to the 5th power is 3,125. X to the 5th times X is X to the 6th. This information to their 7th powers is 6.27 times 10 to the negative 28, which equals my K value. Questions so far?
Do you assume that H2O has molarity if it's like neglected unless it's otherwise stated?
So H2O, if it's given as H2O, it's assumed to be liquid. This is gaseous water or steam, that's when you need to include it. So pure liquid water is excluded from our equilibrium constants because their concentrations don't change appreciably.
Oh, okay.
Yeah, that is an exclusion here. Good question. So once you plug and solve for the, use 6th root and everything, do you guys know how to 6th root on your calculator? Either 6th root like x6 or whatever, or raise it to the 1/6 power as a fraction, it will work. So once you get that, you're like, okay, 5.21 times 10 to the negative 8, pretty dang small, but is it small enough? Let's check. So, holy cow, that's low, right? But then you need to check for your 5% rule, and I should see the checking of the 5% rule on your work. So you take your x value divided by the smallest value you would have subtracted from, which is 0.002 times 100, whatever that is. I know for sure that's less than 5%. Can someone tell me the percent? 0.0026%, right? Yeah? Okay, so much less than 5%. That works. So from there, what would you then do with your x's? What would you do with your x's? Plug it back in to your equilibrium, and you guys can find your equilibrium values. I'm just not going to go back and do that right now because I'm moving on to the harder question. But if you guys want to check, what's your equilibrium concentrations? Anybody? Let's do the iodate. IO31 minus.
Doesn't change.
Yes, that's the point that we're supposed to be seeing. It doesn't change appreciably because it doesn't proceed in the forward direction appreciably. So that concentration initial is really, really close to the concentration at equilibrium. So what a lot of times you'll see is that this is approximately the same molarity because when you subtract 5.2 times 10 to the negative 8, it doesn't even get close to the question, especially if we're considering sig figs. Does that make sense? It does not change appreciably for these two reactants because we're neglecting X, but we will have a value here and here because we have to have a value there because we have to have made some products. So you're plugging your values back in. And those values are not on my paper, right here. You just times it by 5, but you guys can do that. All right, so this next question is one where I think you probably ran into problems, and that's why I texted out yesterday. Is it okay on Sally, by the way? I try to do as many updates as I can via Sally versus my website, because that's I can't do that on my phone. So, and whenever you set this problem, you realize you have 0 reactants. All products, which is kind of an issue here, because what's our value of K? Super duper small, which means what? Which means what? Reactants are favored, not products. So does it make any sense that we have 0 reactants in all products? No, it doesn't make any sense. But you probably didn't notice that at first. And you're going, okay, plug in icebox. I have to subtract from my products because I have 0 reactants. I must add to my reactants because I don't have any. So I add 2x here. 2x, 5 blah blah minus x, 0.06 minus x. So then you're like, okay, this is a neglecting X problem set. Let me neglect X as we go. You should be writing these down as we go because when I take this up, this better be done. Okay, work with me. Your K value, K expression is your numerator, products over reactants. The reactants have to be squared here. So the K value gets here, plug in your values, but neglect your X because we're attempting to kind of eliminate some complex math here. Like, we don't want to do the quadratic formula unless we have to. And so then my 2x squared goes in the bottom. I just kind of walked through my math steps here for a second. So 9.5 times 10 to the negative 13 is equal to that value over 4x squared. Rearrange, divide by 4, square root. X is equal to 9 times 10 to the 4th. How much is that? 90,000. Is X small? Heck no, right? It's like, that's huge. So that should be first the slap in the face that you did it wrong, right? This was almost an exact question similar to this on the AP exam last year. And so my students did the same thing. They're like, well, I can't neglect X. What do I do? And so what you need to realize is sometimes we start off with situations that are not ideal. So this situation started us off with us seeing this reaction, but we poured in a test tube a bunch of the products. So the products are like, I don't want to be here. I need to reverse the reaction. I need to fully react in the reverse direction and make a ton of reactants. Then the reactants can go, all right, I can make an equilibrium reaction happen, but I'm just going to make a couple of products and call it a day. So the first part of this is to make the reaction happen to completion, which is actually a BDA chart. This is why I wanted to do this one with you. So we cannot do it this way. We realize we're wrong. So what we have to do first is take this information and plug it as a BDA, and let's let this thing react first, kind of to completion, and then it's going to go back to equilibrium. So here we go. I have to rewrite this real fast. What's my reaction? C2. And I'm sure nobody did this, so I'm sure everybody's going to be writing with me. Yeah. 2CH4 equilibrates to C2H6 plus H2 gas. So we had 0.6 molar here and 0.52 molar here and 0 here. So before the reaction, no products, no reactants, all products. So during the reaction, basically it's like kind of like a limiting reagent. Like, I have to subtract one of these. Who am I going to have to subtract? Because these both can't react fully. The smaller one. It's a 1-to-1 ratio. This is going to get exhausted, leaving us with a little bit of this and some reactants. So I'm going to subtract 0.06, and add how many over here? Times 2, because it's a coefficient, right? So plus a 2-to-1 ratio of 0.06 molar. So that's 0.12 molar. And then this is 0.46. And this is 0. So before this reaction can actually achieve equilibrium, it must react, because we can't get that equilibrium to work out the way we want to. So once it reacts, we're in a good place to start our equilibrium now. So basically we're doing a BDA, and then we're doing ice. Because now we can let it go to equilibrium to actually have some good numbers to work with here. So at this point, this is my initial for ice. Are you guys with me? You're seeing like the reasoning why we're doing this? Okay. So now, this is my ice, 0, and now I'm going to let this react. Might need my reaction there. So there we go. What do you think I should do now? Subtract how many x's? 2 x's. This one? Plus 1x is a product, right? And plus 1x because it's a product. So 0.120 minus 2x, 0.46 plus x and x. And this information is going to get plugged into what?
Equilibrium constant.
Equilibrium constant expression. So equilibrium constant expression was, what was it? The value. 9.5 times 10 to the negative 13. So K was equal to 9.5 times 10 to the negative 13. And we're doing products or reactants, but these products are, where the x's are included, because the complexity of this math we're going to get to, and the fact that K value is so small, very few of those reactants are going to actually react, right? So the X should be negligible. Very few products are going to be made. X should be negligible. Do I neglect this one? No, because I can't call that 0. It's going to call the whole thing 0, and then we're going to start over. So this gets neglected to 0, approaching 0. This gets neglected to approach 0. So then we get first product here times 0.46. Nothing, no exponents, right? Because those are ones. And then over the reactants of 0.120. Don't use your x's. We still square that. Now the math's like super easy. And so go ahead and tell me what that is when you get there. Anybody? Times. Ooh, so that makes much more sense, right? Something like that? Yeah? Yeah? Thanks. I just need like a second because sometimes butterfingers happen. So that's our X value. And then we need to double check that we're okay to neglect, which you probably will realize it's dang small. And that's much, much, much smaller than 0.12 that we would be subtracting it from, but we just need to double check. So this divided by 0.120 times 100 is what percent?
Less than 5.
Way less, but can I get a number? Alvin, can you take that divided by 0.12 times 100? Anybody?
2.4.
Negative 11%, right? So you're good to neglect there. You're in good shape. Yeah.
Do we just, in a reaction that goes both ways, do we just automatically consider whichever part's on the right the products?
Yes. The way it is written is identifying these are the reactants and these are the products, with the left being the reactants, the right being the products. Even if it is reversible. Yes. Question.
And so you need to do the BDA when you're given only products and not reactants.
Not true. You're only giving products and not reactants for a reaction that does not favor products.
Okay.
Right, so the K value has to be really small. So basically the K value and the what's present initially has to disagree. Does that make sense? So like if I have all products and no reactants and my K value is like very, very, very much favoring the reactants, you have to let the products react to form reactants first and then go to equilibrium. Vice versa, if the K value is uber, uber large and you have, well, yeah, if the K value is really, really large and you have all reactants, you're probably just going to do your icebox and then you'll say, not neglecting X, you'll just find X. Because you probably wouldn't have had a thought in your head to try to neglect if you see a very large K value. Yeah.
Wait, so why can't you go from like C to H6, sorry, yeah, C6, sorry, no, C to H6 and H2 to H4?
So you're saying make these, flip the reaction?
Yeah.
Because whenever they're giving you a reaction, most of the time they will go from that perspective when they are achieving their math. If you did flipped it, I think you would still get the right answer. No, but if you flipped it, you'd have to invert your K value. Yeah, so you'd get the wrong answer. So if you did that, I think they'd probably give you credit because that's pretty clever. But I'd have to double check that the math worked out. But I think it would. But you'd have to invert. If you flip your reaction, you invert your K, plug where you're supposed to. I will try that. That's a good point. I'll try it. Yeah.
Yeah, I was gonna ask, like, when you flip the, like, expression, they put the reactants on top of the sides and the bottom. Cause like we learned, like,
if you-
it reverses.
If you do that, did you flip your K value?
Like,
Or
when
did you try
flip
that?
the K value.
That's what I'm gonna try.
I tried it.
Did it work?
Do you mean like make K negative?
No. K will never be negative. Invert by 1 over.
Oh no, I didn't do that.
Yeah. So
Like, yeah.
let me. I want to try that. That's clever. Thanks. I'm always looking for cleverness. Flip reaction, K value. All right. So I'll try that one more too, and on my own time. But we're not done. What would we have to do with this X value? Plug it into which one? Right here, right? Here, and here, and we'd have our finals. Okay? Alright, so that's enough neglecting X for now. Let's just talk about the process one more time. I have like a little chart of things I wanted to chat with you about. So, generally, we will not be using the quadratic equation. you would generally just solve for x for most of these. So if you can just take the perfect square root of both sides, you're going to take this perfect square root and solve for x, no neglecting, no quadratic, simple math, algebraic expressions. If you cannot take the perfect square root, you have to do the quadratic equation. That's generally when you have a large k value, you're not neglecting. If you can neglect, please neglect. Got it? And you can't cancel the x squared out, meaning you can't take a perfect square root. When do you know that neglecting x is okay? Super small x, or super small what? Okay, that's generally it. But you also need to check your 5% rule. How do you know if you need to go to completion, which means react first? Okay, so when the k value contradicts, and if you get to the point where you've neglected x, and you're like, oh no, it's like 90,000, I can't neglect, right? So when that also contradicts your thinking. Oh, and then also, whenever you have neglected x, which is basically what you said, but when it's just maybe not 90,000, but it's just over 5%, you have to go back and either let it go to completion, or you could do the quadratic equation. And I think that's it. Yeah. Okay. Whew. Let's take a break from me for a moment. Let's talk about Le Chatelier's. Who remembers anything about Le Chatelier's? Give me what you got.
And then like the stress on a system, like zeros to rubber to reduce stress.
Okay, so I'm gonna add one word. He said when you put stress on a system, the direction of flow of the reaction, it will go towards the way that eliminates the stress, but the system has to first be at equilibrium, because once it's at equilibrium, it's in a good place. Once you stress it out, it needs to go back to equilibrium. So it's going to shift left, shift right, or no shift. Use your words, shift, okay? So let's do I'm going to show you this video of the guy, my fave, first. I already showed you that, okay. Because I think it's a good introduction. Write down what you need to first. It's a 7-minute video, and then we'll do some problems with it.
Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 66. It's on Le Chatelier's principle, also referred to as equilibrium law, and it's a really elegant principle that you apply to reversible reactions. And it basically says if there's ever a disturbance to equilibrium, the reaction will move to counteract that disturbance. And so let's say, for example, I'm at an equilibrium state between reactants and products, and I all of a sudden get an influx of reactants, way more reactants. It's going to throw my equilibrium out. And so what can I do? Well, since this is a reversible reaction, I can move the reaction from the left to the right according to Le Chatelier's principle.
So he said add a bunch of reactants. The stress is too many reactants. Well, how do you get rid of reactants? You take them and you force them to react to form products. So you're basically forcing them to react in the forward direction, which is what he's saying right here.
As I do that, I increase the amount of products and I bring it back into balance. That's essentially Le Chatelier's principle. And so according to that, in any reversible reaction where we have reactants and products and it's established in equilibrium, if we ever have a disturbance, and that disturbance could be adding or removing
I don't know if you can see this, but write these down. These are disturbances. We're going to review them as well with our notes. He said the disturbances can be addition of chemicals, which chemicals are a really generic term for both reactants or products. Another disturbance is removal of chemicals. So I'm saying this out loud so you can write it down as well. So that's removal of reactants or products. Changing the pressure or the volume of a system can disrupt its equilibrium, especially if we have gases. Like that's going to be gaseous equilibrium. A lot of times our solutions, who cares? You change the pressure, it doesn't change anything. And then temperature is a big deal. If you change the temperature, especially if it's an endothermic or exothermic reaction is given, it's going to affect our equilibrium. And then dilution, which just basically means changing the concentration. Dilution. He's going to go over each of these two, and we will as well. So changing additional removal of reactants or products, changing pressure or volume, changing heat or temperature, and diluting. Thumbs up if you're good. Okay. Do I need to repeat anything? You guys good?
chemicals, it could be a decrease in volume, an increase in pressure, it could be an increase in temperature, a decrease in temperature, or even dilution. What's going to happen is a new equilibrium is going to be reestablished again. And so let me give you an example of that, a graphical example. If we're looking at the Haber process, where we're taking nitrogen and hydrogen gas and converting it into ammonia, this could be our initial equilibrium, where we have given amounts of concentration of each of these. But let's say at this point right here, there's an influx of hydrogen. So we're increasing the amount of hydrogen. So that means we're increasing the reactants on the left side of the reaction. According to Le Chatelier's principle, the reaction simply moves to counteract that additional reactants. And so which way is it going to move? It's going to move to the right. And so what's going to happen to the amount of hydrogen? It's going to decrease.
How do you see that reflected as on the graph that it moved to the right? So a super like steep slope of react these reactants away, and increased products. There's a positive slope there. Do you remember doing this on your straw lab?
Yes.
Yeah. No. So you say no, we did it wrong. But if we did it right, it's going to look something like this.
What's going to happen to the amount of ammonia? It's going to increase. What's going to happen to the amount of nitrogen? It's going to decrease because it's a reactant as well. And so a new equilibrium is going to be established. And so if we look at this at the molecular level, so this is all of our gases. Again, they're all mixed in together, but we have varying amounts of that. Let's say we get an increase in the amount of hydrogen gas. How can we get rid of that hydrogen gas? We can simply combine it with nitrogen, make more ammonia, and then we can reestablish that new equilibrium again. This also applies to pressure caused by changes in volume as well. And so let's say we're looking at this reversible reaction where we have dinitrogen tetroxide, which is a clear gas, which can move reversibly to nitrogen dioxide, which is going to be a reddish-brown gas. And let's say we put a mixture of these gases at equilibrium inside this chamber right here, and I were to simply decrease the volume. So if I decrease the volume, it's going to be more concentrated, and so we're going to have a darker color. But if you were to watch it for a given amount of time, it'll turn back to that color. And so it's important that we understand really what's going on, and you can't figure it out looking at it this way. Let's look at it at the molecular level. So originally, we had a mixture of those gases that look like that. And why was it reddish, brownish? Because we had enough of those nitrogen dioxides, which are going to be these ones right here, which give it that kind of a color. So what happens when I squeeze it? What happens when I decrease the volume? I'm increasing the pressure of those gases. And so according to Le Chatelier's principle.
Okay, here's a teaching point. Decreasing the volume does what to pressure? Increases pressure. So the stress is not really the decreased volume. The stress is, I'm under too much pressure. How do I get rid of the pressure? Do I shift to the side with more moles of gas or shift to the side with less moles of gas? Because pressure is caused by, give me specifics, collisions that keep the container wall. So if I have less things in the container, I'm going to have less collisions, which is hence cause less pressure. So he's going to say it's going to shift towards the colorless version.
Principle, what's it going to do? It's going to move to counteract that increased pressure. Well, how can it do that? Well, if you look here at the reaction, we've got 2 moles of the nitrogen dioxide on the right side, but only 1 mole on the left side. And so if we can move this reaction from the right to the left, we can decrease the number of moles that we have, and we can alleviate some of that pressure. And that's really what's going on. And it's going to take a little bit of time for that to occur, but that reaction is switching from the right back to the left. This also applies to temperature and energy as well. So let's look at that same reaction. Again, we're taking this colorless dinitrogen tetroxide and moving it into nitrogen dioxide, which is reddish brown. As we move from the left to the right side, that's going to be an endothermic reaction. What does that mean? It actually takes in heat from the surroundings as we move from the left to the right side. And so I'm simply going to add that heat down on the left side, and we can now
I think this is going to be helpful if you do it like this. If you actually say, oh, it's a delta H that's negative, you put the heat on the product side. If the delta H is positive, you think of it as a reactant, and so that's going to help you think of it as a cheap way of thinking of it, but we'll do an advanced way in a second.
Treat it as a reactant. And so what happens if we increase the temperature? If we increase the temperature, if we increase that heat, what it's really doing is it's essentially adding more reactants. It's adding more things on the left side, And remember when we added more hydrogen in that Haber process, what happened? It switched to the right side. So we had a shift towards the right side. What's that going to do? It's going to push our reaction to the right. We're going to get a darker color. And so this is the same concentration of gas, but here and here they've heated it up. And so we're seeing that reaction move to the right side to counteract that increased temperatures. Likewise, what happens if we decrease the temperature? It's like decreasing the reactants on the left side, and now it's going to move towards the left side, and we're going to have more of that colorless gas. And so Le Chatelier's principle is wonderful, and we can apply it, for example, to increase yield. And so let's say we're looking at this Haber process where we have nitrogen gas and hydrogen gas making ammonia. This is an exothermic reaction, and so that means we could put heat on the right side. And so let's say I want to increase the amount of ammonia. Well, let's look at the concentration. If I want to increase the amount of ammonia, what would I do? I would simply increase the reactants. If I can increase the concentration of my reactants, it's going to push the reaction to the right side. I'm going to have more of that ammonia. Let's look at the next one. How could I increase my percent?
I'm done with him for a second. I wanted him to introduce, and we're going to do some examples together. Okay, so in terms of how do we relay our information, if you say that Le Chatelier's principle says the reaction will, or the equilibrium position will shift left or shift right, that's a statement, not an explanation. So if you're ever asked to explain it, that's what I'm here for. So let's go through how do you explain it in terms of rates of reactions and equilibrium positions, and does the K value change? Now, I've previously said that all reactions have one established K value at one established temperature. So hence, what is the only thing that can ever change the K value? If you change the temperature. If you change the reactants, you change the products, you change the pressure, you change the volume, you change the concentration, it will only change the equilibrium position. Like the graph will look differently, the reactant concentrations, the product concentrations will be different, but the ratio will be the same, so the K value will be the same. So the only thing that can ever change the actual K value is the temperature, because it's a new kinetic energy associated with particles. One side is favored, one side is not favored. It will change the ratio itself. So we talk about the stress. Just like you guys like to get rid of your stress and come back to equilibrium, so does reaction. So become one with our reactions, right? So he briefly said adding or taking away a product or a reactant can change equilibrium. Will change the equilibrium position. So I'm going to put like the change equilibrium position over here, okay? So that's something that can change. But why? Like why, what's the explanation behind it? I'll just do one of these for an example. So if I add a reactant species, like increase the concentration, what happens to collisions? They increase, okay, so it increases collisions. So what does that do to and so we're talking about reactants, right? What does that do to the forward reaction? Speeds it up. Okay, so increasing collisions increases the rate of the forward reaction. Okay, so if you increase the rate of the forward reaction, it's out of equilibrium because the rate of the forward and the rate of the reverse are not the same, right? That's the definition of equilibrium. Rate of forward equals rate of reverse. So if we increase the rate of the forward reaction, we're going to make more products. Well, we can't make more products because that's going to change the equilibrium constant itself. So what's going to happen is, oh gosh, we got more products. The products are then going to also collide. They're going to increase the rate of the reverse direction, and then they're going to eventually get its happy medium again, which is called equilibrium. So the process is, as you add a reactant species, the collisions increase. It increases the rate of forward. The products increase, and then it happens again. The products are going to collide and eventually increase the rate of reverse to the point that eventually these come back to equilibrium. But it is a little bit of a cycle, and so as this occurs, you'll see it different. You'll see that it'll look differently on a graph as well. Just like he showed a graph, I'm going to show a graph in a second. But I'm not going to do every single explanation here because it's about acknowledging the background, but not only acknowledging it, but also knowing how to answer the final question, which is which way does it shift? Question? Okay. So one thing he didn't say was that you can actually remove a reactant or product by precipitation. So if I add something called a common ion to a solution, it can cause one of the other ions that was in solution, it can cause it to precipitate. So let's say I have a solution of sodium chloride. What are the two ions in there? Sodium ion and chloride ion. Let's say I add another external reagent that's not a part of my equilibrium. Adds silver nitrate. What's likely going to happen if I add silver nitrate? Who precipitates? The chloride precipitates, right? It's going to make silver chloride as a precipitate. So, hence, I added silver nitrate that wasn't in the equilibrium, but I affected equilibrium by doing what? Okay, so I added a common ion, but what did it effectively do to the equilibrium equation, the stuff in the equilibrium? When I precipitate out silver chloride, what happens to the concentration of chloride? It goes down. So I effectively decreased the concentration of chloride. And if chloride were a reactant, which way would I shift? Towards the reactants, right? So if chloride were a product, it would have seemed as if I removed a product, so I would produce more products. So just think of it as an after effect is the decrease of the chloride concentration, but what caused it was the addition of a common ion that would have forced the precipitate to occur. We'll do a lab with this on Monday, so I think this will make much more sense then. Okay, and then a couple other things. Gaseous equilibrium deals with mostly pressures, right? So partial pressures go into a Kp expression. So I didn't say this earlier, but this changes the equilibrium position. Okay, so back here, changing pressure. We know, we kind of talked about this already, decreasing volume changes pressure by increasing it. It's an inverse relationship with Boyle's law. Whenever you have a difference in moles, so his example was 1 mole of product, or 1 mole of reactant gas yields 2 moles of product gas. When I change the volume, it's going to change the pressure. So, as a quick example, increasing pressure, the pressure is too high. What do I want to do? What do I want to do to get my process back to equilibrium? Shift left or shift right here? Why? Okay, so I want lower pressure, and that's going to be from less moles of gas, right? If I want to get my pressure back down, less moles of gas would be shift left. If my pressure were instead decreased, what do I want to do? Because that's my stress. I need to fix my pressure. So you want more pressure, and no, this is pressure, not product. Sorry, that's pressure. I want more pressure, so I need that. That's going to come from more moles of gas, and so that would be a shift right. Yeah.
What if the moles are the same on both sides?
No shift. Right. So if there's an equivalent number of moles, there is no favorability because there is no favored side at that point. The only other part that you'll ever see is adding an inert gas. For some good examples of gases that are unreactive, non-reactive. Water vapor would actually be usually a reactant, or it would be something that could affect this. So do you guys know what I mean by inert gases? Noble gases, right? Noble gases are fairly unreactive. Who? Argon, neon, helium, krypton, xenon, thank you. Those would be inert gases that would not change the equilibrium. So one second. The reason why is because if I add another gas, the gas pressure increases, right? So then you're like, oh, gas pressure increases, do I shift? The reason that it doesn't shift is because that inert gas is not included in the equilibrium expression. It's not in the equilibrium itself. Also, if I increase the pressure total by this addition of gas, the pressure total changes, yes. But the partial pressure of each gas that's actually in the equilibrium expression or in the equilibrium reaction, partial pressures then don't change, or the partial pressures don't change, which don't change the ratio. Or even if the partial pressures do change, they're changing by the same amount, therefore the ratio doesn't change. The ratio of reactants products are still the same. And so that's why adding inert gas doesn't change anything. I got 2 more things to tell you, then we're going to do an example. So catalysts, which we learned about already, what's their job in a reaction? Stand up if you're getting sleepy. I know it's Friday. Say again. They lower the activation energy, so they change the pathway, effectively increasing the rate of reaction. Now, they increase the rate of reaction. The whole class stands up when she says it now. So, if I increase the rate of reaction, I don't only favor one direction of increase, I favor both directions of increase. So it speeds up both the forward and the reverse direction, so it does not change equilibrium. It doesn't change the equilibrium position either. Okay? So if there's no change in equilibrium position, we call that a no shift. So if I say, adding a catalyst does what to my reaction? Nothing. It just makes both reactions happen faster. But we're not talking about rate, we're talking about equilibrium position. This is the one, this is the big boy right here, temperature. So far, I've basically said the equilibrium position changes, like the graph changes, look, the products and reactants change their relative locations, but the ratio stays the same. So nothing so far has actually changed the K value. Everything has changed the equilibrium position, which means just the relative concentrations. But here's where the here's where the K value will change, is when temperature gets involved. Because at this point, we definitely need to know the enthalpy reaction, so we'll know if it's endo or exo. And so we'll also, from that point, that perspective, we'll call it heat as a reactant or heat as a product. But what's happening is that one side of the reaction is able to achieve faster rates, and the other one doesn't have a chance because there's not, like, it's energy given. It's not able to meet its activation energy as quickly. So there's a lot of energy components here. It's unidirectional. I'm going to do an example with this. So this is the part you might write down a couple of items here. I'll give you a second to read them on the top. What curve is this? Say it again? Maxwell Boltzmann curve. Because I heat up a reaction, more particles have more energy, and they're more likely to meet their activation energy, which the activation energy is the part under the line right here, and then more particles under the curve are able to meet activation energy. So as I increase the activation, or increase the speed of the particles, more of the particles from one side of the reaction are likely to meet activation energy. So they're going to force their side of the reaction to occur. And so the phrase that's utilized to explain this is that increasing temperature favors the endothermic reaction or endothermic direction. Now, the endothermic direction can be either way if you think of heat as a reactant. So whenever let me write this example down. A plus B yields heat plus C. If I increase the energy of a reaction or increase the temperature, it's going to favor the reverse direction. The reverse direction is the endothermic reaction because I'm utilizing heat as a reactant in the reverse direction. Does that make sense? Question?
Why is it the temperature, like increasing temperature can change it, but increasing like pressure, then increasing the temperature from the pressure?
It won't happen. Pressure and temperature are related, but we fix the pressure so the temperature doesn't change. You know what I'm saying? Like if I increase the pressure, immediately the pressure comes back to equilibrium by decreasing the pressure, by shifting to the side with less moles. So there's not a chance for the temperature to increase. This is like a permanent temperature change.
Yeah.
Okay, let's talk some more. Yeah.
So, like, when the guy was talking about it, he was talking about, like, shifting left to right, but that's not to accommodate for, like, it's not shifting left to right, so it's at the same K value, the actual K value is changing.
For this one, only yes. So, no, he is saying in the video for everything else except for temperature, we're shifting left and right to get our products and reactants back to their ratio, which is meeting their K values value. So when we shift left or right, we're changing the products over reactants back to where their equilibrium position is, so that their K value is the same. Because the K value cannot change if they're at equilibrium, unless we change the temperature of the reaction. Okay, so as you can see in this particular example, if I increase the temperature, it's going to favor the reverse direction, right? So favor the reverse, gosh. Okay. Reaction. Okay, so if I do that, what concentration increases and what concentration decreases in terms of products and reactants? Okay, so product concentration decreases and reactant concentration, okay, increases. What happens to my K value? Does it increase or decrease? Say again? Decrease, like decreasing a numerator, it decreases. Increasing a denominator, doubly decreases, right? So they agree with each other. So the K value is smaller when you increase the temperature of a exothermic reaction. Question.
Are these type of things simultaneous, or is it like a mechanism like the products will increase very significantly from there?
It's usually so quickly it is simultaneous. But you know it has to be mechanism because we talked about kinetics. We're just not focusing on that aspect. Good question. Okay, so this is for an exothermic reaction. All right, so what if I said for this reaction, instead of increasing temperature, the same reaction I've written here, I decrease the temperature. I decrease temperature, tell me my process. Yeah.
Your products would go up.
Give me baby steps here. So I want to really understand the molecular level.
So it favored products.
Why would it favor products?
When you decrease it, it favors the exothermic reaction.
Okay, decreasing it favors the exothermic reaction. Let me add to that, okay? So basically, we're still talking about kinetics just a little bit in the background. Like the background noise we're hearing is the kinetics. Decreasing the temperature means that this reaction over here, the reverse reaction, doesn't have enough energy to occur. That's likely not really going to be occurring. But this side of the reaction has enough energy to do its job because it doesn't require heat to occur. Does that make sense so far? This side's like, heck yeah, I don't need heat. I don't care if it's cold or not. I'm still able to occur at a reasonable rate. This side's like, I need heat. I'm not going to be able to occur. I don't have enough energy. So the rate of the forward is going to increase where the rate of reverse will decrease. Sorry, I'm like really abbreviating with weird letters. So if I increase the rate of the forward direction and don't increase the rate of the reverse direction, products will be favored. And that's what Nikki said, but I wanted to kind of get the connection there. So products are favored, and if products are favored, what's going to happen to my K value? It's going to increase because concentration of products will increase and reactants will likely decrease because I can't make products without reactants being consumed. And so the K value would change. That's the only one where the K value changes. Okay, you guys have your packet? Let's do the one. I think I have one question in there. I could just have you pull up your packet for no reason, but I think I have my questions in there. It's got phosphorus, trifluoride, and something else in there. Oops. All right, so here's our example. Go ahead and do that in your group. Tell me, does it shift left or shift right? And then how will the change, or how will chlorine gas change? And we'll check these. Shift left, shift right, no shift, and then also the change. Take 5. That's all I hope you'll need. It might not be in your pocket. It might just be on the board. So I will make sure it's in your pocket or not. Nope, not in your pocket. Nope. One person.
Yes.
you guys write down your reaction so I can scroll down?
Yep.
Yes. Sorry, the last thing is volume. I'm just gonna grab a laptop. Levi, you want to do it? Just grab a laptop while I'm gonna check this, or log into a desktop. We're gonna do a simulation after this.
Yeah.
Are you presenting today? Are you presenting today?
Yeah.
Can I come watching you? I see you sit next to Kyle.
Yeah.
I'm sure that's great. Chemistry and all. All right, team, just kind of get logged into the laptop. I'll show you where we're going quickly on there, but I know they take a little while to get logged on. Checking this now. Oh, I'll wait for Avery to get back. She's a good citizen. Getting all the laptops for her lazy table over here. Yes. All right, so just get logged on for me because you know the computers are a little slow. Sean, that means you have to open the laptop. Okay, so PCL3 is added. What do you guys say?
Oh, shift right.
Why shift right?
I'm sorry.
You're right.
Okay.
Shift right.
Okay.
Why shift right?
Before we
We are on PCL3. What are you talking about heat?
What? I was just talking.
Okay, dinosaurs and kind of stuff. Okay, we're just talking.
Okay,
All right,
so
so
shift right, you add
so-
more reactions, so you make more.
okay, but I just want to hear a little bit more than that. So I'll do the first one. Shift right because the rate of the forward. If I can not combine my words here. Rate of the forward increases. So as you shift right, increasing rate of the forward increases because there's more collisions from the particle's perspective of the reactants. It's going to increase the rate of forward and then eventually get back to equilibrium. What's going to happen to Cl2 concentration? Increase or decrease? Decrease because it's being consumed, right? You're consuming reactants as you form products. Okay? PCl3 or PCl5 is added. Shift left, and that's because the rate of reverse is increased, okay? That's just a side note, just making sure you're thinking about the collisions. And what's going to happen to Cl2 gas? Cl2 gas is increasing, thank you. Some participation would be great here because we're going towards the reactants, we're going to make more of them. Temperature is lowered. Okay, so I want to hear some details. We said shift right, which is true.
Okay, because it's an exothermic reaction. Because it's an exothermic reaction, that means that.
Alvin's going to pick up. Alvin. You guys are awesome. Levi. Huh?
There's less collisions, so the rate of the reactants combining slows down. So that means less products being made, so products have to increase in order to maintain the equilibrium.
Very good. I'm gonna put that in fewer words if I can. So rate of reverse slows down, right? Because it's an exothermic reaction, ET on that side, so that's going to slow down. So the rate of forward speeds up, right? And as that occurs, we're making more products, and as we make more products, that's because of the shift right. As we're making more products, what happens to Cl2? Decreases Cl2 because we're shifting right. And what happens to K value? Because this is the change of K. Increases because we're making more products, consuming reactants, K value should increase. Okay, good. PCl3 is removed. I'm going to stop the explanations between now. You guys tell me the final answer here. PCl3 is removed. Shift left, and then concentration of Cl2 increases because you're making more products. I mean, reactants, making more reactants. And that neon is added?
No shift.
Okay, no shift because it's a inert gas. And then volume is increased. What does volume do to pressure? Decreases pressure. Oh no, the pressure's too low. What do I need to do?
There's 2 moles of gas in the left.
So we're going to shift left to make
4.
2. Is it 2?
Yeah, because it's the
Okay.
VCO 3.
2 mole of gas versus 1 mole of gas. Yeah.
So like, doesn't inert gas just have no collisions at all?
No, it actually increases the collisions of everything. So there's like an equal change in rate of both sides, so there's no change. That's what I said earlier. It's an increase in the total pressure. That is a true statement. It also very well, it's likely not going to change the partial pressures of everything because partial pressures are the moles of gas divided by total moles of gas times the pressure total. So remember the mole fraction, partial pressure. So the ratio will stay the same basically as you compare it to the total pressure, which increases. So even if the total moles increase and the total pressure increases, they basically negate each other. So the partial pressure of the gas shouldn't change. So when you plug it into K value, the K value doesn't change, the equilibrium doesn't shift. And yeah, even if it does change, it's changing the same ratio. So the ratio of products versus reactants doesn't change. Okay, go to my website. Go to Unit 7. I had a graph. I can do the graph on Monday. And some miscellaneous stuff I have for you guys on Monday. I'll do that on Monday. Okay, so let's see if this pulls up for us. We have about 25 minutes. I'm hoping to get the shockwave stuff done in my classroom because I have the computers for you now. Give me a thumbs up if you've already pulled up my website. Just making sure I know where we are. So when you're there, where's my website? Not up for here. You'll see it says Equilibrium or Le Chatelier's WebQuest. It's got it's actually an inquiry lab that because the College Board puts out 16 inquiry labs and we have to do a significant portion of them. We also have to do labs 30% of our time together. That usually means 1 to 2 labs a week, right? Really heavy in Unit 1, 2, and 3, not so heavy in Unit 4 and 5. Kind of like trickling them in and out. So I'm a proponent of following instructions. So I follow the instructions of College Board to make sure that we're legitimately teaching AP chemistry. So what you'll see is that this first part is very similar to an inquiry lab, but we're not doing the inquiry lab. We're doing the pre-lab section just to get an idea of Le Chat's, and then we're going to do a fun lab on Monday with Le Chat's. So the first section you see down here, the WebQuest information's here. The link is here. The link that's in the WebQuest is not going to the correct place, so this is the link you'll use. So when you open this up, and this as well, this is the thing you see first. It'll say in the instructions, scroll down to the general equilibrium section right here. And these are the animations. They work for me well in Firefox. So if you're opening it up, I think it works well in Firefox. Is it opening? Are these little simulations opening? Could you possibly click on that and try that if you guys get there? So bromine, cobalt chloride, nitrogen dioxide, and so forth. They're working awesome. Okay. So they're not working for some people. If they're not working for you, go to Firefox and then hit like allow extension or plug in or something like that. And my file's taking about an eternity to open. This says what? I don't know if you have the power to install Shockwave. That's the only thing.
So is it a new thing called WebQuest?
Yes, it's called Le Chatelier Investigation WebQuest Student period.
Yeah.
And then opening up the document and then that link as well under the document, and you guys can talk and work together, that's fine. It has some good reading, some background knowledge of information that relates to your blood oxygen levels, that because they have they significantly do try to include real life examples. So the readings here are important. The simulations, animation 1, 2, and 3 are what I think you should do in class right now. Now. And then you'll read some at home. You'll see some other examples with reading. This is a highly involved reading example. And then it has some other websites here you'll do. You'll look at the stresses, explain to me stresses, and then some examples from a test that I used to use that I'm not using anymore, but these test questions are really good. We'll check these test questions on Monday. Expect them to be done, okay? So you have 20-ish minutes left in class. finish your web quest, finish your lab, and then these 4 questions from the Chatliers. So I gave you guys time to work on your lab already, so I feel confident to do that at home. But the web quest, do the simulation or the animations right now. I gave you hugs. I'll give you guys kisses on Monday.
The conversation notes. The ones with the short conversation notes.
Come on, people.
I got it.
Emma, do you have?
Thank you.
You guys need it usually. So it does say to pull up the link from my website. When you click the link on the actual web quest document, it's not opening correctly. So that's why I put this link additionally right here. And that link right there gives you information to go to the animations under general equilibrium here. So just let me know if you guys can't find what you're looking for. All right, all you. And I'll play some Post Malone.